Okay, so today's lesson is going to be continuing what we did yesterday, but jumping straight into using kinematic equations to solve problems involving projectiles. So not really using images as much as we did yesterday. So before I get too ahead of myself, there's only 3 problems that we're going to be working on. The first 2 I'm going to do with you guys is an example, and the last one is going to be a try. And what you're going to notice is that none of these problems are exactly alike. In physics, you're going to have a variety of variables that you know and a variety of variables that are unknown. And really the commonality between the different problems is going to be the thinking skills, the problem solving skills. It may not be the exact same process, but the way you think about the problem is going to be very much so the same. So keep that in mind when we're going through these examples, that you're not trying to remember steps as much as you're trying to commit memory to the process. So a ball is projected horizontally from the top of a 92-meter high cliff with an initial speed of 19.8 meters per second. Determine the horizontal displacement and the final speed of the ball the instant prior to hitting the ground. So I drew a quick sketch of what they've described, and I'm going to start marking it up. So I'm trying to figure out what the horizontal displacement is going to be right as it's hitting the ground. So according to that picture, this last dot that I've drawn is the point right when it's hitting the ground. So I'm trying to find this distance here. We can call it x for simplicity's sake. The other thing I'm trying to find is my final speed. So I'm going to change colors here. My final speed just before it hits the ground. So the ball is going to be moving in this direction. At this point when it hits the ground, I'm trying to figure out what's the magnitude of this velocity. That is going to be my final speed. So the information they've given me is they've told me the cliff is 92 meters tall. So I can at least go ahead and label that the cliff is 92 meters tall here. They've also told me that the ball is launched horizontally with a speed of 19.8 meters per second. So horizontally means directly to the right, not at an angle, 19.8 meters per second. Now, in the beginning of these notes and kind of throughout, what we've done usually is we used tables. So we talked about, at certain moments in time, what is the x position and what is the y position. And we've counted our points, figured out, at time 0, what's the position vertically and horizontally. At time 1, what's the position horizontally and vertically. And that's helped us. Now, at time 0, that's the easiest point to figure out because, your positions are starting at 0. So I should say here at this dot, both my x and y initial positions are 0 meters. That's going to be helpful. What I really need to figure out is what is my time going to be when this ball hits the ground. If I can figure out my time, that's going to help me figure out this x position, and that may help me figure out my final speed. But I'm just going in order. I want to figure out my horizontal displacement, which is this x position at that unknown time. So I don't know what x is right off the bat, but I do know what my y final position is going to be. When it reaches the ground, it will have fallen all the way from the top of the cliff, a full 92 meters. So my y position is technically going to be negative 92 meters. Now I can use this information to figure out time. Let me show you how. When we were talking about y position, the equation that we used for finding position was always for accelerated motion. So change in position is equal to 1/2 at squared plus VIT. And we talked about if the initial vertical velocity is 0, we can always ignore this term. Now, according to this diagram, this ball is not launched upwards or downwards, it's just launched to the right. So my initial y velocity is 0 meters per second. So I can ignore that term in red. So I'm going to start plugging in some of my known values for my vertical displacement. I know that my change in position, my delta x in the y direction, is negative 92. I know that this is going to be equal to 1/2 times my vertical acceleration. Now vertically, this ball's on Earth, so it's falling at the acceleration, of gravity. So I'm going to say it's falling negative 10 meters per second squared. Now my time is my question mark. That's my unknown. So that's the variable that I still have. So I'm going to simplify this and solve for time. So I'm going to have negative 92 equals negative 5t squared. I'm going to divide both sides by negative 5. When I do that, I'm going to plug that in my calculator off screen. Negative 92 divided by negative 5 is going to get me 18.4, and this is equal to t squared. Now I'm not trying to find t squared, I'm trying to find t, so I've got to square root both sides to do this. So when I take the square root of 18.4, I end up getting a time of 4.3 seconds. So I can fill in my table right here. My time is 4.3 seconds. So how does this help me? Because I wasn't asked to find my time. Well, finding my time is going to help me fill in the rest of this table, because now the only value that's missing is x. And when the only value that's missing is x, that means I can use some of my kinematic equations that involve time. So horizontally, my projectile is moving at a constant speed. This means that I can use the equation final position equals velocity times time plus initial position. Now remember, initial position, we don't have to plug into the equation if it's 0. And if I look back at my diagram, the ball starts at 0. So I'm going to ignore that term when I'm problem solving. So my final position, I don't know. But I know that my velocity for the ball is 19.8 meters per second to the right, because it's going to go at a constant speed. And now I know the time that the ball is going to be moving, because after 4.3 seconds, it's going to hit the ground. So when I multiply 19.8 times 4.3, I end up getting a final position of 85.1 meters. So now I can fill in this table with 85.1 for my final position. Now my final position horizontally is the same thing as my horizontal displacement. So my answer to letter A is right here. Now I'm going to direct my attention to letter B. Letter B is asking for the final speed, the instant prior to hitting the ground. So if I were to draw that velocity vector, redraw it over here. This velocity vector is at an angle. It's got an x component and it's got a y component. Now, since projectiles go at a constant speed horizontally, if it has an initial speed of 19.8, that means my x component is going to be 19.8 meters per second. My y component, I need to solve for that. I need to figure out how fast is this ball going to be going downwards when it gets to the ground. So if I look at some of my other kinematic equations that I had at the beginning of the notes, there's one equation that stands out. V final equals acceleration times time plus V initial. The reason why I like this is because my V final is going to be my y velocity. The other reason why I like this is because V initial is a term that I can ignore if my initial vertical velocity is 0. And look at that, my initial vertical velocity in the diagram is 0. So I can ignore that term. So I'm going to plug in my known values. I don't know my final velocity, but I know that vertically my acceleration is negative 10, and I know that the time right before it hits the ground is 4.3. So when I multiply those two values, I end up getting negative 43 meters per second. This is the y component of my velocity. So now that I have an x component and a y component, how can I use these to find my velocity? Well, hopefully you're seeing a shape when you look at the velocity, the x component, and the y component. It's making a right triangle, and right triangles follow Pythagorean theorem, where your hypotenuse squared is equal to the sum of your legs squared, otherwise known as a squared equals b squared plus c squared. So I don't know my velocity, but I do know that my horizontal, or my x component, is 19.8, and I do know that my y component is negative 43. So I can plug this in my calculator, 19.8 squared plus negative 43 squared, and I end up getting a very large number. So v squared equals 2,241 meters per second. And this is a squared value rather. Sorry, I shouldn't have put my units there. It's meters squared, second squared. Now, I'm not trying to find velocity squared, I'm just trying to find velocity. So I'm going to square root both sides. When I do this, the square root of my answer, oops, not the cube root, the square root of my answer is 47.3 meters per second. So this is my final speed of the ball. Boom. So the skills that we used here was really the data table and figuring out, okay, how can I fill in as much information in that data table as possible, and really letting that guide us through the problem. So let's practice that skill on the next example. So determine the launch speed of a horizontally launched projectile that lands 26.3 meters from the base of a 19.3 meter cliff. So I'm being asked to figure out what's the launch speed. I'm going to fill in what I know. They told me that the cliff is 19.3 meters high. And they told me that the ball lands how many meters? 26.3 meters away from the base of the cliff. So that's how far horizontally it goes. So if I were to make a table, just like I did above, oops, maybe not X, Y. Don't like how I drew that. Time, and we've got X, and we've got, maybe I should make that a little bit bigger, and we've got Y values. At time 0, my ball is at position 0 for X and position 0 for Y. I don't know what time it's going to hit the ground, but I know that at that moment, I'm drawing it really bolded right here, this is the moment it hits the ground. It's going to be at a horizontal position of 26.3, and it's going to be at a vertical position of 19.3. Now, once again, if I can fill in this table, that might guide me through figuring out the launch speed. The launch speed is really, what is this velocity right here, right when it gets launched off the cliff? What is the magnitude of that velocity? So I'm just going to let the table guide me. I'm going to figure out what is that time right when it hits the ground. So if I wanted to use my X position to figure it out, here's what I need to do. My X final is equal to velocity times time plus X initial. But I'm going to color this X initial red because if that X initial is 0, I can ignore it. And according to my diagram, yeah, X initial is 0. So I could ignore that term. However, the other thing I need is velocity right here. I don't have velocity. That's what I'm trying to solve for. So this is my tip to my brain. This is the clue to my brain that I can't use X to find my time just yet because I need that velocity. I don't have it yet. So I'm going to direct my attention instead to my Y component. And since Y is accelerated motion, the equation I use is this: change in position equals 1/2 AT squared plus VIT. And remember, VIT we color in red because if initial velocity is 0, we can ignore that term. Now, looking at my diagram, since the ball is launched horizontally, it has no initial y velocity. It's 0, so I could ignore that term. Now, do I know my acceleration? Yeah, it's on Earth. It's going to accelerate -10. Do I know my time? No, that's what I need to fill in my table. But don't know my change in position vertically? Yes, I do. My change in position vertically is 19.3. So I'm going to plug in everything I know and solve for my unknown, which is time. So when I do this, I should say negative 19.3 is my position because it went down 19.3. When I do this, I need to simplify. So I'm going to have negative 19.3 equals negative 5t squared. I'm going to divide both sides by negative 5. So negative 19.3 divided by negative 5 gets me 3.86. This is equal to my time squared. So to figure out my time, I'll square root both sides. So the square root of 3.86 gets me a time, gets me a time of 1.96 seconds. So I'm going to plug this into my table right here. Now I have a nice complete table. 1.96 seconds is when the ball is going to hit the ground. Now, why is this useful? Let me tell you why. This is useful because now I know my horizontal position, which is XF, and I know my time, which is T. I know that initial position is 0, and I can solve for my unknown, which is V, which is my launch speed. That's exactly what I've been trying to do this whole time. So I'm going to plug in what I know. 26.3 equals V times 1.96. I'm going to ignore that initial X position because it's 0. And I'm going to take 26.3 and divide it by 1.96. When I do this, I get 13.4 meters per second for my velocity. Now this is my launch speed because it's going at a constant speed horizontally. So if this is how fast it's going just as it hits the ground, what I mean how fast it's going horizontally when it hits the ground, then that's how fast horizontally it was going right when it got launched. Now, once again, it's not the same exact problem. The only thing we had in common was making that table, reasoning our way through it by filling in that table with as much information as possible and letting that table really guide us through the problem. So now you guys pause the video and try this last problem without me. Okay, if you've unpaused the video, I'm assuming that you've attempted the problem and you're ready to check to see if you did it right or get an explanation. So a soccer ball is kicked horizontally at 15.8 meters per second off the top of a field house and lands 33.9 meters from the base of the field house. Determine the height of the field house. So I'm going to fill in my information. I know that it gets launched 15.8 meters per second. And I know that when it hits the ground, it is 33.9 meters away from the base of the house. I do not know how tall the house is, though. This is an unknown. That's interesting. It's not letting me write. There we go. That is an unknown. Some other things that I know. I know that my initial X position is 0. I know that my initial Y position is 0. I also know that vertically, my initial velocity is 0. So these are just helpful things to know going into the problem. So I'm going to make my table to guide my thinking. So I know that at time 0, my positions are 0, right? I don't know what time it'll be when the ball hits the ground, but I know that when it does hit the ground, it's going to be 33.9 meters that it's traveled horizontally. Now, I also don't know how far down it fell. I don't know what its vertical Y position is going to be. So I'm going to try to fill in the table with as much information as I can. So let's start by trying to find time. So I'm going to use my constant velocity equation. And remember that this xi can be ignored if my initial position is 0, which in this case it is. So I'm going to plug in what I know. I know that my final position is going to be 33.9 horizontally. I know that my velocity is 15.8 meters per second. It's going at a constant velocity horizontally. My time is the one thing I don't know. So I'm going to divide 33.9 by 15.8. When I do that, I get 2.15 seconds for my time. So I'm going to fill this into my table right here, 2.15 seconds. So how is this helpful? Well, now that I have my time, I can figure out what my Y position is going to be by using my acceleration equation. Change in position equals 1/2 AT squared plus VIT. Remember, VIT can be ignored if initial velocity vertically is 0, in which case it is. So I'm going to plug in. My change in position is an unknown, actually. I'm not going to plug in anything. I don't know how far it falls vertically, but I do know that my acceleration on Earth is -10, and I do now know that my time is 2.15. So when I plug in 1/2 times -10 times 2.15 squared, I end up getting a change in position of -23.1 meters. So what does this mean? This means that when the ball hits the ground, it will have fallen 23.1 meters. So what does that mean about the top of the house? That means my house is 23.15 meters tall. 23, I'll just limit it to 1, 23.1 meters tall, and I'll even highlight it. How high is the house? Well, this is how high the house is. So hopefully you got an idea of what I meant by the skill that we're talking about. That table is a very, very powerful resource. But remember, not every problem is going to be exactly